All right, Honors Pre-Calc students, this is Mrs. Cook. We are going to learn section 1.3, which is evaluating limits. Now, actually, what I'd like to do to start this one out is I think that you are capable of doing example A and B here in example 1 from our last summative quiz. So I'd like you to pause the video, work through these two, and then list two things that are the same that you found, and maybe a couple things or at least one thing that's different that you found. So seriously, pause it because you don't want to watch me work through this. Pause it, and then when you're ready, you can go ahead and press play. And then let's see what you did, and we can talk about what's the same and what's different. So I found that this one had a hole, a removable discontinuity because of these factors that I could remove, and therefore after I removed them and I plugged in the 1, I got the limit to be 3. Here, this was nice. This guy was continuous, and so the limit also was 3. So the same thing that I found was that the limit for both it was equal to 3. I also found that the graph ended up being a parabola for both. What I found being different is that A is not continuous because of that removable discontinuity. But B was definitely continuous. Okay, so taking a look then at the graphs, just a little blast from the past reminder. I thought I'd just remind you from first semester or even from Algebra 2. I did x equals negative b over 2a to find the location of the axis of symmetry there. And then when I plugged that back in, I was able to find my vertex. And I just plugged in a couple points to the left and a couple points to the right to figure out what was going on. And again, you can see that the graphs are almost the same. Just have that hole right there that is the difference. So how does this relate to what we're doing? Well, the above functions are actually called functions that agree. So I'll write these down because this is important. We're going to need this terminology. These are functions that agree at all but one point. These two functions here, this x cubed minus 1 over x minus 1, and then this function here, x squared plus x plus 1, are called functions that agree at all but one point. So in the next example, they want me to find the limit, identify two functions that agree in all but one point. So there's that terminology again. So once again, just go ahead and pause this, work through this problem, take a look at the graph, and then we'll summarize the two functions that agree in all but one point. Hopefully you just paused it, took some time to try this on your own. I found that the limit was going to be equal to -5, and I found that there was a hole at -3, -5. But what does the graph look like? Well, actually, I can go ahead and just graph this function, x minus 2. So it'll be a line that begins at -2, and the slope is up 1 over 1. So I'm going to get this line, but notice this line is going to have this hole. So the limit is still -5. That y value, we're approaching from the left -5, and we're approaching from the right -5. So we get a line that has a hole in it. So this is not continuous. All right, so we could say that then f of x equals x squared plus the x minus 6 over x plus 3, the function that they gave us, and f of x equals what we had left, that x minus 2, are functions that agree at all but one point. Now, when we take a look at example 3, our ideas change completely. Here, we are going to find the limit if it exists, and much like what we've been doing, the first step that we should be thinking about is plugging in. Now, if I plug these in, I'm going to get that 0 in the denominator, which does not make me happy. In fact, I'm going to get a 0 in the denominator, and in this case, I'm going to get a 0 in the numerator, so we call that indeterminate. When it's indeterminate, I'm going to use that method of plug, which I just did. Didn't work, so now it's time to play, and then we'll plug in again. How do we play with this? That is a brand new concept in this section, 1.3. So to do this, I need to get rid of the square root of x plus 1 minus 1 in that numerator. And one way that we've talked about doing this before is called the conjugate. So I'm going to give that a star note. I'm going to have to multiply the numerator and the denominator by the conjugate, which would be the square root of x plus 1 plus 1. And so I would like you to work through that so you don't have to watch me do that. In the numerator, we're going to be FOILing first, outside, inside, last. And in the denominator, you're going to go ahead. You can distribute or you can keep those. Let's keep those factors separate. Did you see what happened when I FOILed in the numerator? Square root of x plus 1 times square root of x plus 1 just gave me that x plus 1. So I end up getting these, the last terms, that plus 1, the minus 1 to cancel. And then I was able to get these x's to cancel. So I end up getting this simplified form of the function. So they're asking me really for the limit as x approaches 0 of 1 over the square root of x plus 1 plus 1. And in this case, this is one of those functions from the original one that is a function that agrees in all but one point. These two functions agree in all but one point. Now we did the play part by multiplying by the conjugate. Let's go ahead and plug in again. So when I plug in again, I get 1 over the square root of 1 plus 1, and that's just a 1. My limit is 1/2. Let's go again here. Let's try that idea of the conjugate, because when I plug in here, I'm in some trouble. Nothing exciting happens. I get that indeterminate, 0 in the numerator, 0 in the denominator. So let's multiply by the conjugate, square root of 2 plus x plus the square root of 2 in the numerator and in the denominator. And I'll keep that denominator separate terms, but I'll FOIL the numerator. Try it. What happened? I ended up getting that function to be, the reduced function to be 1 over the square root of 2 plus x plus root 2. So when I plugged it in as 0, I got a nice neat answer. Well, written very sloppily, 1 over 2 root 2. Or you can certainly rationalize the denominator since we're kind of used to that. You don't have to do that though. Okay, if you look at this example, these are the ones that we actually already covered a while back, but they were not assessed on our recent test because we hadn't had enough practice with those. So we want to do those again, and to do those, we're going to be using the facts that are written right here in this box, these remember pieces here. So these are two limits that you have to have memorized. This one I just want to make note is the same thing as the limit as x approaches 0 of cosine x minus 1 over x. So these can be in either order. We could talk about why that is. It's because you would have that -1 factor that you could pull out front. So either way, you're still going to get 0. All right, so let's take a look here. We're looking for any of these things in the box. So let's go ahead and we'll split this guy up. And I'll do that by taking the limit and I'll break out that 1/7 times the sine of 2x over x. Okay, so now I am able to say, let's bring this 1/7 out front, and let's have this argument here match this denominator. To do that, I'm going to multiply the numerator and the denominator by 2. So take a look where we're at here. We have 1/7 times the limit of 2 sine 2x over 2x. Well, this guy right here, we can use since we have this memorized up top in that box. It doesn't matter what my x's are here, as long as they're matching, my limit will always equal 1. So I know that this right here is just, the limit of that is just equal to 1. So right now, I end up having that 2 that I can also bring outside. So I get 2/7 times 1, and my limit is 2/7. On to the next page. Okay, can we take a look and try to get some of those things in the box again? This time, let's factor out a 3. And when I do that, I'll get 1 minus cosine x over x. That 3 coefficient, well, the limit of that is just a constant 3. So I can bring that out front, and in this case, I end up getting a 3 times that's 0. Remember, you'll have to have this memorized. The limit of that is 0. So the limit in part D is 0. We're trying to find those things that we have memorized from the box. So in this case, if I change this to a cosine of theta over 1 times a tangent, well, let's see, tangent is sine over cosine. And then I also have a theta in the denominator, so I could write it like this. Okay, we don't maybe recognize anything just yet in terms of memorizing, but I do see something super nice that happens. This cosine is going to cancel that cosine. And look, just what we have left is the limit as x approaches 0 of sine theta over theta, which we have memorized is equal to 1. Along those same lines, let's write tangent squared as sine squared over cosine squared. And let's see how we could write that. If we're dividing by x, well, that's the same thing as multiplying. Instead of writing it as dividing by x, let me go ahead and multiply it by 1 over x. So how can you split this up so that's things that we can actually evaluate when the limit is equal to 0, or we can plug in 0? I have right now the limit as x approaches 0. Well, let's definitely take one of those sine x's over x's because I've got that down. And then I'll have another sine x over cosine squared. Let's think about that. We know this is 1. And cosine squared in the denominator is actually very friendly because I can go ahead and plug in a 0 and I don't get 0 in the denominator. The cosine at 0 is just 1. So this is just saying 1 squared. So I have sine of 0 in the numerator is equal to 0. And then the cosine, this is just 1 squared. That is really just 1 times 0. So my limit is 0. Okay, we're getting there. I'm trying to rewrite this one. It's a lot like identities, blast from the past. We haven't done those in a couple of chapters. I'm going to get a common denominator here in that numerator, and you'll see that I'm dividing by a fraction. So if I switch up colors on you a little bit here, I can say instead, let's multiply by the reciprocal, which is cosine x over x. And that's really nice because that's outside the parentheses. So it gets me some things to cancel, right? Take a look. I have 1 minus cosine inside the parentheses. So then that goes and cancels that cosine. I have that memorized piece. This is the limit as x approaches 0 of 1 minus cosine x over x, which is in